Good afternoon, students. So today we are going to cover the radio frequency telemetry system. So in the last class we have seen the landline telemetry system, but and also in the end of the last class we just seen the overview of the radio frequency telemetry system. So in the landline telemetry system, as we have seen that there is a physical communication path between the transmitter and the receiver. Means the measuring end and the receiving end, the receiving end, there is a physical path. But in this radio frequency telemetry system, the communication path between the transmitter and the receiver is a wireless communication. That communication is a wireless communication. Now, when we are going for wireless communication, we may send the information in terms of the frequency or in terms of the pulse format. In terms of the frequency or in terms of the pulse format. Now the question comes that when you are going to send the information, how you are going to send the information using the wireless communication path, either in terms of the frequency or in terms of the pulse format. So the thing is, when you are trying to send the information using the frequency format for long distances, we are going with the modulation technique. So long distances means nowadays they are going to use the wireless communication between the transmitter and receiver. If at all the distance between them is more than 1 kilometer, instead of using the wired communication, they are going with the wireless communication, because there are some drawbacks when you are using the wired communication, because whatever the path which we are using, the communication path, it should be get protected from the external noises, all those things. Okay, now in order to avoid that one, and if we are satisfying with the wireless communication, we'll go with the wireless instead of the wired communication. Okay. So here in the wireless communication, when you are considering the wireless communication, obviously we will come across one terminology called as a modulation technique. We are come across one terminology called as a modulation technique, and in the modulation technique there are three different types of modulations. One is means basically the three different types: amplitude modulation, frequency modulation, and the phase modulation. So whatever the modulation it is, when you would like to send the information using any one of those modulation techniques, you are supposed to know. Means you are supposed to focus more on the frequency band, means the bandwidth which is going to be used by that particular technique. Okay, the bandwidth. When you are sending the information from one point to another point, obviously you are supposed to be allocated with certain frequency band. Otherwise, you can't send the information, because you are supposed to take the permissions from the higher authorities in order to use a certain frequency band for the long distances when you would like to send the information. So at that time, obviously you are supposed to pay some amount of money for that particular frequency band in order to allocate that frequency band to you people. Okay. So here, if we are using the frequency modulation, let us suppose I'm using the frequency modulation. For that, the bandwidth for the frequency modulation is calculated using the formula 2 into beta plus 1 into FM. So we least bother about the formulas which we are using. In case of the amplitude modulation, it is going to be the 2 FM. So we least bother about the formulas, but we are only bother about the frequency bandwidth which is allocated for a particular channel. So if we are using only one channel, then no problem at all. The frequency band means only one bandwidth is going to be allocated. Then you can send the information. So if at all you would like to send the multiple channels information, means I'm having the multiple transducers and I would like to measure the multiple variables, the parameters like temperature, pressure, as well as some mechanical issues, mechanical components which you are observing using the transducers. I would like to send all of them from the transmitting end to the receiving end, from the transmitting end to the receiving end. So as we know that there is a separate frequency band should be allocated for each channel. So if you are going with the basic one, then separate frequency band should be allocated for each channel. So if you are going to keep on purchase the separate frequency bandwidths for each channel, then obviously the cost of the system is going to be increases. Obviously the cost of the system is going to be increases. Let me take the simple example what I took in the last class. The thing is, when you are going to use any DTH communication or any cable communication, that is a TV cable communication, at that time you are not paying the separate, means you are not having the separate cable paths, or you are not having the separate DTH antennas for each channel. Means we are receiving the TV channels which are in the hundreds range. Means more than 100 channels we are receiving using only one path. If it is a cable connection, we are using only one communication path for all the channels, not a separate paths for each channel. In the same way, and when you are going for the DTH also, so for the DTH, Also, we are using only one antenna, one DTH antenna, but not the multiple DTH antenna which are going to be used as a separate DTH antennas for each and every channel. It is not like that actually. But the DTH antennas are going to be changes from one brand to another brand. Like we are having the Tata Sky, we are having the Videocon, we are having the Airtel, we are having the Idea. Means the DTH channels are different DTH what is that companies are there, but they are using only one communication path for all the channels. They are not going to use separate path for each channel. If they are doing, then definitely we are supposed to pay a lot of amount for watching what is that, hundreds of channels. Okay, so that's why instead of what they are doing is as the frequency allocation is plays a major role. Whenever we are having the separate means separate DTH communicators like Tata Sky, Airtel, they are going to be allocated they are going to be purchased a frequency band for their DTH. For their TDH, they are going to purchase one frequency band. In that frequency band only, they will send all the channels. In that frequency band only, they will send all the channels. Now the question comes up: how they are able to send the information using only one frequency band? Of course, there is a separate frequency which is allocated for each and every channel internally. But if you are taking the DTH, for the DTH, only one spectrum is there. Using only one frequency spectrum, they are sending the information. They are sending the hundreds of channels information from the transmitter to the receiver, means in our homes. Okay, so the thing is how they are able to send the information, means multiple channels using only one frequency spectrum is the question. So there it comes, we come across one terminology called as a multiplexing. We come across one technology called as a multiplexing. Multiplexing means using only one path we are able to send the multiple channels information. So I'm not going with the transducers right now. I'll go back to the transducers, but just realize the concept in the realistic manner. So we are having the 100. Let us suppose I'm using the 100 channels. I would like to allow those 100 channels through a particular frequency band So at that time, how we are able to send the information means it is a multiplexing operation. So multiplexing means there are two different types of multiplexings are there. One is a frequency division multiplexing and another one is a time division multiplexing. So here, as per our syllabus, I'm going with the time division multiplexing. So in that time division multiplexing, I'm going to use one thing called as a pulse amplitude modulation. Means the information is going to be transferred in the pulse format. I'm using the pulse amplitude modulation to send the information, but they're using the time division multiplexing concept. I'm able to send the information. Now the question is, what is the time division multiplexer? Is a question. So when you are using the time division multiplexer, we are having on the board. So here I'm assuming that I'm having the three channels. I would like to send the three channels information from the transmitting end to the receiving end. If you see this one, these three channels are going to be passed through the same path. Means a common path is going to be used between the channels. But this particular common path is not going to be continuously allocated a particular channel. It is going to be allocated each channel for a time period. So after that time period, it is not going to be allocated to that channel. It is going to be allocated to the next channel. After that time period, it is going to be allocated to the next channel. After the certain time period, it is going to be allocated to the next channel. Means if I'm having the three channels, first channel is going to be, let us suppose three channels are there. Three channels need to be transferred through the communication path. Then what I'm going to do means I'm going to have the three time periods. During the first time period, this particular one, this block is called as a commutator. This block is called as a commutator, and this block is called as a decommutator. Commutator is the one which takes the responsibility to send the different channel information through a particular communication path. Means this path is there, but this path is not available continuously for each and every channel. This particular path is going to be allocated for some period of time to the channel 1, after some period of time to the channel 2, after some period to the channel 3. So if you see this one, I'm having the three channels now. So I'm creating the three intervals. In the first interval, I'm sending the first channel information. Look at this. This is the first channel information. These two are the intervals for the channel 1. Means in these two time intervals, I'm not sending, means the channel 1 is not going to be send the information, because this connector is not connected to the channel 1. It is going to be connected to the channel 2. In the second time interval, channel 2 is going to be sent the information, and this is what we are having. And in the third time period, this particular pointer is going to be connected to this particular third channel, and the information is going to be transferred from here to here. If you see this one, 3 channels are having the 3 time slots. During the first time slot, channel 1 is sending the information. During the second time slot, the channel 2 is sending the information. During the third time period, the channel 3 is sending the information. Okay now. So once the channel 3 is over, again the channel 1 is going to be gets this particular communication path. Channel 1, after that the channel 2, after that the channel 3, and this processes keep on sending. In this way, we are using only one communication path, and using one communication path we are able to send the multiple channels information, because each channel is not going to be stay on this particular path continuously. Each channel is getting some time period. Now the question comes that when we are having the time period for each channel, how the information is going to be transferred perfectly from the transmitter to the receiver. So we are having the antennas like a normal cable connection for the TV, as well as we are having the DTH. Even though we are able to see only one channel, do you think that only one channel is going to be received by the antenna? It is not like that actually. Multiple channels are going to be received by the antenna, and we are having the set-top box. Inside the set-top box, depending on our channel option, only one channel is going to be driven as an output from the set-top box, but inside the set-top box, multiple channels are there. Inside the set-top box, multiple channels are there. Now the question is, all channels means whenever you are changing the channel, immediately you are going to see the channel, but you can't see any difference. Means you can't see any lags. It is going to be hard for some period and coming other channel, because they are going to allocate the time period in the microseconds and the nanoseconds range. Means you can't see that shifting from channel 1 to channel 2, channel 2 to channel 3, channel 3 to channel 1, and go so on. So you can't see that one with your naked eye. So that is the advantage for this particular communication. Means here that we are using the time division multiplexer concept in the pulse amplitude case. Time division multiplexer concept in the pulse amplitude case. Time division multiplexer means we are not using the common path between the transmitter and the receiver continuously for a particular channel. The common path is going to be used by the multiple channels. Now the question comes that how much time period means how much time period is allocated for each channel is going to be decided based on what? Means based on what they are going to decide how much time period should be allocated for the channel 1, how much time period should be allocated for the channel 2, how much time period should be allocated for the channel 3. As we have taken the 3 channels on the board, let me take the 3 different signals. So I am assuming that this is my y-axis and this is my x-axis. I am representing the 3 different variables. Okay now. 3 different signals. So this is a time period for the signal 1. It is a y-axis only. It is a time period. It is also time period. Means I would like to compare. So assume that this is my first channel signal. Assume that this is my second channel signal. Assume that this is my third channel signal. Least bother about the amplitude. Only bother about the time period. Only bother about the time period. So if you see this one, if I am going to means how the time period is going to be allocated means, if you see this one, assume that it is a channel 3, it is a channel 2, it is a channel 1. Channel 3 is continuously varying, means the variation of the amplitude of the channel 3 signal is a small period of time. Within a small period of time, the amplitude is keep on changing. If you see this one, channel 2 is taking more time, means the channel 2 signal is taking the more time to change its amplitude, and channel 1 is taking more time to take the change compared to the channel 2 as well as the channel 3. So whatever the channel whose information is changing very fast, that channel frequency is going to be taken as a sampling rate. That frequency channel is going to be taken as a sampling rate. In this case, if at all, I am assuming that it is not the assumption. By seeing the diagram, you can easily comment that this signal is varying continuously with a small period of time, within a small period of time. But this one is varying, but it is taking some period of time. This one is also varying, it is taking some period of time. Now, in order to, if I am allocating some t period, let us suppose this is a t1 time period, it is a t2 time period, if it is a t3 time period. If I am taking the t1 time period for sampling, means whenever there is a variation from here to here, if I am going to take this one as a sampling period, within this variation we are having so many of variations in the channel 2 and many variations in the, means the signal is varied a lot in the channel 3. So if we are taking the T1 as a sampling period, then we are going to lose the actual data from the channel 3 as well as the channel 2. If we are taking the channel 2, channel 1 is going to be gives the information because the channel 2 time period is very less compared to this one. That's why whatever the variations are there in the channel 2, we can capture that one as well as the channel 1. But again, we are missing the channel 3. That's why when we are going to decide how much period, means how much sampling, with how much speed the sampling should be done. Sampling is nothing but pointer is allocated for the channel 1, for the channel 2, for the channel 3. How much means with how much speed the allocation of this path for each channel, individual channel should be changed. That we call it as the sampling rate. We have seen the sampling theorem, right? Sampling theorem is nothing but in order to avoid the actual losing of data, we are supposed to focus on how fast, I'm redrawing this one, how fast the signal is changing. How fast the signal is changing. How fast the signal is changing. Based on this fastness, we are supposed to decide the sampling period. We are supposed to decide the sampling period. Okay, I'm having the sampling period. Wait. We are supposed to decide the sampling period. Okay, so we used to call it as a sampling rate. This period is called as a sampling rate. So this sampling rate purely depends on the signal. Means when we are having the 100 signals, out of 100 signal, which signal is varying very fastly, that signal is, value is taken for the sampling rate calculation. So which signal is what changing its value very slowly, that is going to be the least, but which one is varying, which signal amplitude is varying very fast, that one is taken for the sampling rate calculation. Based on that only, this this particular arrow is going to be keep on changes from the channel 1 to channel 2, channel 2 to channel 3, channel 3 to channel 1 again. Okay, so whatever the signal whose frequency, whose variation is very fast, that signal frequency is taken for sampling operation. Remember, in general case, in case of the pulse code modulation, in general amplitude, in general modulation cases, the sampling is going to be done based on the Nyquist rate. The sampling is going to be done based on the Nyquist rate. Nyquist rate says that sampling is nothing but what we have seen one thing, right? So means we are having the channel 1 information, channel 2 information, channel 3 information. These channels are going to be sampled, and this whatever the signal which is going to be sampled, that is going to be passed to this wire, like this. Okay, like this. So this sampling means it is just like a switch. It is just like a switch. This switch is going to be open, close, open, close, open, close. How fast this switch is going to be open, close, that purely depends on the sampling rate. This sampling rate purely depends on how fast the a particular channel signal is varying. I'm taking the channel 3 because the channel 3 signal is varying very fastly compared to the channel 2 as well as the channel 1. So if I'm assuming, if I'm taking the channel 3, if you are going with the Nyquist rate, the sampling rate should be greater than or equals to the twice the highest signal frequency. I'm assuming the Fs is the highest signal frequency. So 2Fs, this is the sampling rate in the normal cases. Sampling rate in the normal cases. But if you are taking this one in this what is sampling rate? Sampling is going to be done by the commutator. Sampling is going to be done by the commutator in the in any time division multiplexing. So again, allocating these samples to the corresponding channels is going to be done by the decommutator. We will just bother about this one right now. We only bother about the sampling rate, how the sampling rate is going to be decided. So this sampling rate is in the normal communication case, but this one is called as the Nyquist rate. But in case of the telemetry system, this sampling rate is greater than the 5 times the maximum frequency. Maximum frequency means, if you see this one, this signal is varying very fastly. Time period is less, means the frequency is more, So whatever the signal frequency whatever the signal whose frequency is more, that signal frequency is taken for calculating the sampling rate, and that signal frequency, this sampling should be done. This opening, closing the switch, this opening and closing the switch, or moving the commutator from one channel to another channel, one channel to another channel. The time period is going to be decided based on the sampling rate. This sampling rate is 5 times the maximum sampling of this particular signal, maximum signal frequency, maximum frequency of a particular channel, say a particular channel. That particular frequency is taken for calculating the sampling rate. Calculating the sampling rate. That too, this is the 5 times the maximum frequency. It is 5 times the maximum signal frequency. This is 5 times taken only in the telemetry system. Remember this one. It is in the telemetry system, not in the what we say in the normal normal time division multiplexing. But in case of the telemetry system, the this particular sampling rate is 5 times the maximum frequency of a particular signal. So let me take one simple example which is there in the material which I sent you. So let me show you that one. So look at this one. Look at this. Here we are assuming that we are having the different channels. We are having the different channels. For example, he took the channels of 8 channels. This is assuming that 8 channels are there. As I said, the sampling rate is going to be decided based on, as I said, the sampling rate is going to be decided based on what? Based on the highest frequency of a particular signal, highest sampling frequency, highest frequency of a particular signal. So in this case, I am assuming that the highest frequency component, highest frequency means how fast the signal amplitude is varying, how fast the signal amplitude is varying, that is the highest frequency. I am assuming that the highest frequency of a particular channel is 40 Hertz. Highest frequency of a particular channel is 40 Hertz. If it is 40 Hertz, what could be the sampling rate? It is 5 times, na? 5 times the highest frequency means 5 into 4. 540 ja, it is going to be the 200 times. Means this signal is going to be sampled. In this case, if I am taking some multiple channels, and in those multiple channels, one channel highest frequency is 40 Hertz. The channel information is changing with a frequency of 40 Hertz. Then the sampling is going to be done 200 times per second. Means this one. So whatever the diagram which we have seen, this commutator is going to be sends the channel 1 information, channel 2 information, channel 3 information. Means if I am taking the channel 1 only, it is going to be samples this particular channel 1 information 200 times in 1 second. 200 times in 1 second. Just like that, this one is also going to be done 200 times in 1 second. Just like that, this one is also done 200 times in 1 second. Okay, now means this arrow mark, whatever the pointer which we are having, it is going to be get rotated through the channels 200 times per second for each channel. 200 times per second each channel. In this case, we are having the 3 channels now. 200 samples per each channel per second means 3 channels means 600 samples. 6 into 200 samples, totally 600. 3 into 200 samples, totally 600 samples. 600 samples are going to be done by the this commutator. 600 samples are going to be done per second by this commutator. Okay, so because of that, you can't see that variation when you are having the multiple channels. Even though you are having the multiple channels, they are going to be transmitted using the time division multiplexing. You can't see that variation because it is a very fast rate. With a very fast rate, the signal is going to be sampled and transferred to the signal is going to be sampled and transferred to the what we say, I forgot to remember this time. Okay, signal is sampled and transferred through the medium. Okay, so here if you are going into the textbook which we have seen, in this case, based on that information, as we don't have the board, it is very difficult. So based on that information, here if we have one channel with a 40 Hertz of frequency, then 200 samples are going to be done by the commutator. If at all, just like this, means if at all we are having the 8 channels, then for one channel 200 samples, for 8 channels it is going to be the 8 into 200. Each channel is going to be just the 200 times sampling. 200 times each channel is going to be sampled per second. So 8 channels are there. Total samples which are passing through the communication path is going to be the 8 into 200. It is going to be the 1600 samples which is going to be done by this commutator. Look at this. By this commutator, it is going to be since the, if I am assuming that there are 8 channels, it is going to be since the 200 samples per each channel. So this one is called as a commutator. Commutator is nothing but which samples each channel based on the sampling rate. That is going to be decided by whom? That is going to be decided by the developer only. He is going to decide how many channels we are having and which channel information is frequently varying. That channel frequency is taken for calculating the sampling rate. Again, I am saying that in the telemetry system, the sampling rate is going to be 5 times the highest frequency variation of the signal. Highest frequency signal. Okay, remember that. It is 5 times the frequency of the highest frequency signal. Okay, highest frequency signal. So here we are having the commutator now. Wait. Now, if you see this diagram clearly, commutator is sampling. Let us suppose it is only the 3 samples for the explanation point of view. So here we are having the commutator. This commutator is having the unique signal for synchronization. In order to synchronize this commutator with the decommutator, because with how much speed the commutator is sampling, at the same speed the decommutator should desample, means should receive the information, send the information to the respective channels. So in order to synchronize these two, we are having one synchronization signal between the commutator and decommutator. Means the commutator is going to be informed the decommutator with how much frequency it is sampling, so that the decommutator is going to be adjust its frequency to the same frequency with how much frequency the commutator is working. So here if you see this one, 3 samples, let us suppose per second 3 samples are going to be done. Then first sample is taken from the channel 1, and remaining 2 samples period is going to be the ideal for the channel 1. And here for the channel 2, second time period is going to be allocated for the channel 2. First and the last one is going to be the ideal. And channel 3 is going to be takes the last sampling time. First 2 channels are going to be the ideal. If you see this one, 3 different signals are going to be transferred from through this particular transmission medium. Means we are using only one frequency spectrum for sending the different channels, information, but that path is going to be used by the channel, means that path is not going to be used by all the channels at a time. It is going to be used for every time period. Means it is the sampling rate. Based on the sampling rate, it is going to be used by the respective channels. At the decommutator, it is taking the responsibility. If you see this one, first one is in the red color, it is transferred to the channel 1. Second one is the blue color, transferred to the channel 2. Third one is in the green color, it is going to be transferred to the channel 2. Okay. So this is what we are having the time division multiplexing. Time division multiplexing means in order to send, see, if we are not using the time division multiplexer, the frequency band which we are supposed to allocate for sending the multiple channels is going to be more. For each channel, we are supposed to have the separate frequency band. We are supposed to have the separate frequency bands for each channel. In order to avoid that particular the frequency band allocation, separate frequency band allocation, what we are going to do is we are going to use only one frequency band. Using that frequency band, we are able to send the multiple channels information using the sampling theorem or sampling theorem concept. With the help of the sampling theorem concept, using the time division multiplexing, we are going to send the information from the transmitter to the receiver. Okay. So based on this only, we are having the concept called as a pulse amplitude modulation. Basic concept of the pulse amplitude modulation. Okay. Sima, remember, commutator is nothing but the sampler which samples the signal. Decommutator is nothing but, again, it is a desampler. Receives the information serially, and that information is going to be transferred to the means. Each information is going to be transferred to the perfect channel. Okay, that is going to be done by the decommutator. So if you see this one, this is the pulse amplitude modulation. Means the information is going to be transferred in the pulse format. The information is going to be transferred in the information is going to be transferred in the pulse format. Okay. So if you see this one, as I said, we are having the multiple transducers. One for measuring the temperature, one for measuring the flow, flow of liquid, one for measuring the pressure, one for measuring some mechanical issues, one for measuring different types of parameters which we are interested to measure. So for that, we are having the multiple transducers. For example, if we are taking the aeroplane or if we are taking the satellite, from the satellite, it means we install the multiple transducers inside the satellite and we send the satellite to the space. So from the space we are receiving the information, means as we are having the multiple transducers, they are going to be send the information using this concept. One of the example is this one. Okay, means multiple transducers which are residing or installed inside the satellite. From there, the commutator is going to be residing inside the satellite. It is going to be samples the each channel information and sends that information through the medium. Sends that information through the medium to the transmitter. If you see this one, the information is going to be sampled and it is going to be sent in the pulse format. It is going to be sent in the pulse format. Actually, I took one sampling case, but that much is not required. I have another document, but that much is not required as of now. So just remember that samples are going to be, means the commutator is going to be samples the information using the sampling rate, based on the sampling rate, and they are using this particular commutator using only one path, and this information is going to be transferred to the transmitter, and the transmitter is going to be converts the information, means the information is going to be modulated in the transmitter block, and that modulated information is going to be transferred via the wireless communication. This is the antenna at the transmitting end. This is the antenna at the receiving end. This antenna is going to be receives the signal through the wireless communication, and receiver is going to be what it will do. If we are using the modulation demodulation concept, it is going, obviously we are supposed to use the modulation demodulation. It is going to be demodulates the signal, whatever the signal which is demodulated. That demodulated signal is transferred to the next level, and this one is going to be frame synchronization. Here we are not showing the decommutator. The decommutator is the one which is going to be included next to the receiver, That one takes a responsibility to separate the information to different displays. Means we are going to use the multiple scales to see the information. We can't see the temperature information on the pressure scale. We can't see the pressure information on the temperature scale. We can't see the flow value on the temperature scale. Okay, multiple scales are there, multiple displays are there. That is going to be taken care by this particular block. Okay, so here we are having the multiple signals. They are going to be sampled by the commutator, and that sampled information, which is in the pulse format, PAM, pulse amplitude modulation, which is going to be transferred through the transmitter and finally to the receiver finally to the displays. If you want, you can use the recorders also for recording the information, whatever the information which we are observing. To record that one, we may use the recorders also over here. Okay, now. So this is about pulse amplitude modulation. Okay, next case is a pulse code modulation. Pulse amplitude modulation means we are simply sampling the input information. And we are converting that sampled information into the pulse format, The next case is a pulse code modulation. Pulse code modulation is nothing but it looks like a pulse amplitude modulation, but there is a slight difference. In the pulse code modulation, the information is going to be whatever the information which is sampled by the commutator. That information is not going to be transferred in terms of the pulse format. That information is going to be encoded into the binary format, binary 0 and binary 1, and that particular binary format information is going to be transferred using the transmitter. Means it is just like a framing operation. All of us know that scenario, right? Framing operation is nothing but a group of bits are formed along with the extra bits. That information is going to be transferred from here to the next level and so on. Okay, now if you see this one, this is the explanation for pulse code modulation, basic explanation for the pulse code modulation. So in the pulse code modulation, the information is not going to be transferred in the pulse format. Instead, the converted pulse signal is means the sampled pulse signal is converted into the binary format. The sampled information is going to be converted into the binary format. How the information is going to be converted into the binary format is nothing but that purely depends on what is the minimum voltage and what is the maximum voltage which we are experiencing among the channels. Minimum voltage is let us suppose, for example, I am having the 0 voltage is a minimum, and maximum voltage, maximum amplitude of my transducers. I am having the multiple transducers now. Maximum voltage of those transducers, if I am assuming that it is a 5 volts, then 0 to 5 volts. We know that what is the digital, analog to digital communication transmission conversion, analog to digital conversion. Same concept is going to be used over here. If you see this one, what they are going to do means the encoder is the one which takes the responsibility to convert our pulse format information into the binary format. Our pulse format information into the binary format, that purely depends on what is the width of the encoder. What is the width of the encoder means whether it is whether this encoder is a 8-bit encoder, whether this encoder is a 16-bit encoder, 10-bit encoder. That purely depends on the encoder. So how many bits are going to be generated, that purely depends on the encoder. That too, this encoder, choosing a particular encoder, 8-bit encoder, 10-bit encoder, 12-bit encoder, purely depends on how fast this information is changing, with how much voltage the information is going to be changes. Let me take one simple example. We have seen this one in the analog to digital conversion case. So the example is, we call that one as a resolution. So sampled one. I'm assuming that it is a time period. Obviously, it is the amplitude. Okay, it is the amplitude. Assume that my amplitude is a 5 volts. Maximum amplitude is a 5 volts. Minimum amplitude is a 0 volts. Maximum amplitude is a 5 volts. Minimum amplitude is a 0 volts. Okay. Assume that we are having the 5 channels instead of 3 channels. Okay, let me take the 3 channels only. So for 3 channels, I'm assuming that it is a 3 volts. It is a 0 volts is the minimum, maximum is a 3 volts. Means maximum voltage that is going to be varied by a particular transducer which we are using over here is a 3 volts. Okay, maximum voltage that is going to be converted. Physical information which is converted into the electrical signal, that electrical maximum signal is a 3 volts. I'm assuming it as a 3 volts. Okay. For example, each channel, what I'm doing is I'm slicing this one into the 3 parts. I'm slicing this one into the 3 parts. So 0 volts, 1 volt, 2 volts, and 3 volts. I'm assuming that each channel is varying with this step size. Means, for example, I'm taking the 1 degree centigrade. For every 1 degree centigrade variation in the temperature, I'm assuming that the output of the transducer is varying with 1 volt. For every 1 degree variation in the, for every 1 meter variation, if at all you are going with the displacement transducer, which is a LVDT. For example, if for every 1 centimeter variation, there is a 1 volt output. Transducer now 1 centimeter is a distance that is converted into the 1 volt signal. Okay. So at that time, what will happen? This is going to be satisfied. 0, 1, 2, 3. For example, one of the channel is changing its value. Assume that one of the channel, I am assuming that one of the channel is a pressure. Yeah, let me take one of the channel which is one of the transducer which is measuring the pressure. For every 1 kilo, I am assuming that this one of the transducer is varying for every 1 kilo Newton per meter square variation in the pressure. It is changing the output as a 0.5 volts. It is changing the output for every 1 kilo Newton meter square variation in the pressure. The output voltage which is converted by the transducer, the output voltage is a 0.5 volts. This is the step size of my transducer, but this step size, this already allocated step size is not matching with this one. Already allocated step size is not matching with this one. Then what we are supposed to do? We are supposed to increase the samples. This one is a 1 volt sample now. So this 1 volt sample is not satisfied one of the channel. This 1 volt sampling is not satisfied by one of the channel. One of the channel means one of the transducer. Then in order to satisfy this one, because we are interested to satisfy all the transducers information, we are interested to observe all the transducers information. We are not giving the priority to a particular transducer. We are expecting that, we are expecting perfect information from all the transducers, and we are not interested to lose a small variation, a small variation observed and transferred by the transducer. Okay, now we are not interested in that. So because of that, how fast the signal is changing, that signal is going to be 0.5 volts. Now with that rate we are going to be sample. Means instead of taking the 1 volt sampling, I am going to take this one as a 0 volt, 0.5 volts, 1, 1.5, 2, 2.5, 3. Okay, means this sampling is going to be increased. This sampling is going to be increased. When the number of samples are increasing, then the encoder choosing of encoder is going to be changes. So if it is a 2-bit, previously 3 samples, 0, 1, 2, 3, total 4 samples are there, then 2-bit encoder is more than enough. But in this case, the samples are increased. The samples are increased. 1, 2, 3, 4, 5, 6, 7. 7 means I can take the 3-bit encoder. 3-bit encoder means how many samples we are going to get? 8 samples. So 7 falls under the 8 only, na? So means the, what is that, encoder, the size of the encoder is going to be decided by the sampling. Purely depends on what? Sampling. Okay. So here what we are supposed to do means, whatever the number of transducers which we are choosing, how fast means, again here the encoder value purely depends on converting the pulse format into the bit format, purely depends on what is the step size of each change, each signal change. Step size in the sense one transducer step size may be the 1 volt, 1 volt, 1 volt. Another transducer step size may be the 0.5, just like this one, 0.5 volts, 0.05 volts, 0.5 volts, 0.5 volts. Another transducer step size may be the 0.25 volts. Another transducer step size may be the 10 millivolts. That purely depends on the transducer step size. So depending on the transducer step size, we are going to convert the, what is that, pulse information into the bit format. That is going to be done by the encoder. So here encoder is nothing but samples the samples the input signal voltage and converts the input signal voltage into the binary bit combination. Converts the input signal voltage into the binary bits combination. Now, for example, I am taking the 5 volts range, 0 to 5 volts. It is a 5 volts range. Okay. So here what I am going to do is, for example, I am not going with the transducer phase, I am going with the bit size of the encoder. If I am using the 10-bit encoder over here, so as per your textbook we are using the 10-bit encoder, so you may use the 8-bit encoder also. So here the 10-bit encoder means, 10-bit means what? 10-bit representation. All of you know this one, right? We have seen this one from the 3rd semester in the microprocessor. 10-bit means how many samples we are going to get, or how many combinations we are going to get. Combinations means 10 zeros to 10 ones. How many combinations? 10 bits and the total number of combinations are 2 power 10. All of you know, right? 2 power 10 is nothing but 1k. 1k is nothing but what? 1024. But as it is started with the 0, this 1024 is varying the numbering from 0 to 1023. 0 to 1023. So means 0 to 5 volts range is sampled into, what is that? 1024 times. Sampled into 1024 times. Means 5 volts by 1024. If you do this one, if you do this calculation, let me take the calculator for this division. Five by 1024 means 4.8 millivolts. It is going to be the 4.8 millivolts. So 5 volts by 1024. If you want, you can take the 1024, or if you want, you can take the 2 power 10 minus 1. Generally, we used to take the 2 power 10 minus 1. 10 minus 1. Then it is going to be the 1023. Okay. Then a small variation is going to be observed. 5 by 1023. Yeah, this is a very small variation. Okay, it is going to be the 4.8 millivolts. Means each step size is going to be this case. This case, each step size is going to be the 4.8 millivolts. 4.8 millivolts, and totally 10224. 0, if you start with the 0, it is going to be the 1024 samples. And in terms of the what is that values, binary for combination format, it is going to be the 1023. Means each step size is the 4.8 millivolts. 4.8 millivolts means for every signal 4.8 millivolts variation, it is going to be converted into the equivalent of binary combination. If you are having the input signal voltage is a 0, then the output is going to be the 10 zeros. If we are having the input signal voltage is a 4.8 millivolts, then the output is going to be the, what is that, 1. 1 is nothing but what? 430, sorry, totally it's going to be the 9 zeros 1. 0, 0, 0, 0, 0, 1, 2. I'm not considering all. D9 to D0 if I'm considering D1, D2. It is going to be the 10-bit combination 0, 0. For the first 4.8 millivolts, it is going to be the 1. D0 comes under the D0, it is going to be the 1. In the next case, double this one means it is going to be the 9.6 millivolts. 9.6 millivolts means 0, 0, 0, 0, 0. This one is the 0. This one is going to be the 1, 0. Okay, means input signal voltage, if at all the input signal voltage is observed as a 4.8 volts, then the output of the encoder is going to be the 9 zeros with the 1. If the input signal voltage of the encoder is 9.6 millivolts, then the output of the encoder is going to be the 8 zeros 1 0, 8 zeros 1 0. If it is a thrice, and so on. If the input voltage is 5 volts, if the input voltage of the encoder is 5 volts, because we took the maximum voltage of 5 volts now. If the input encoder is of 5 volts, then the output is nothing but all ones of the 10 bits. All ones of the 10 bits means 10 ones are going to be exist.